Got this? Oops. Got this? Yeah? Yeah, okay, so we're going to have a look at magnetic fields, a bit like with electric fields, the formulas and things like this, definitions and unit and so on. So you already know what a magnet is. There is one there. So you have experience of magnets from life, from middle school. You know what they are. So we have an electric field. So what exactly is a magnetic field? Well, it's really the same thing. It's the area around the magnet in which there's a magnetic force. Moving electric charges can make a magnetic field. Magnetic fields can usually be seen by magnetic flux lines. At all times, the direction of the magnetic field is shown by the direction of the magnetic flux lines. So in other words, it's a bit like an electric field. You have the lines around it where the force is, and the direction shows you which way the field is moving, which way, we'll get to that in a minute. You got this, KJ? The whole thing? So in the exam, if there's what is a magnetic field, you're going to say it's a thing with a thing and a thing around the thing.
Yeah. It does the definition.
Yeah, but you're not great with your definitions. No comment?
Good.
In the last show, Oscars.
Say what?
Oscars.
Oscars? No. No interest in that. Okay. Mhm. Yes. Okay. So let's have a look at some of those magnetic fields, which of course, as you've seen in the exam, they'll ask you to draw. So the first one we'll draw is what we have here, the bar magnet, a north-south magnet. So please note that we go from north to south. And this is the shape of the magnetic field. You got this? Yeah. You drew this now. In the exam, this has been and could be a question. Okay, so the first one is a bar magnet. Um, by the way, could we ever just have a north by itself?
Yes.
No. North must always be paired with a south. So we'll never have a diagram with just a north point and a south point. It has to be a pair, like here, north-south. Okay, next one. This is the Earth's magnetic field. Now, maybe I'll draw that here on the side to help a little bit. So, when we look at the Earth, we think of this as the north and this is the south, but in fact, it's really the other way around. Where's my pen gone?
Do you mean towards Australia? No?
Well, what I mean is, we are about here. So what I'm saying is, this is actually, if it was like a bar magnet inside the Earth, it's like the south is here and the north is here. Now the reason makes sense, because if you have a little magnet, north-south, the north will want to point to the south of the magnet, because north and south attract. So when we talk about the North Pole, where Santa Claus lives, as you know, this is actually the south part of the magnet which is inside the Earth. So that's just something to be careful about. And the diagram is the same. It goes around like this. So there's a nicer one there. So you can see the south is here and the north is here, and it goes from north to south. Whoops. Again, they could ask you to draw the one for the Earth. And what they are looking for when they ask you to do this is, well, if you think about it, it's asking you to draw a bar magnet again, right? But what they're testing you is if you know that the arrow should start from the bottom, because the north is down the bottom, not at the top. Yep. Yep. Okay. Continue. Yep. Right, so the next one is interesting, because what you have here is a current. Well, here there's no current, and all the magnets point to the north, Santa Claus's hometown. Then, when the current is turned on, all the magnets point and circle around the wire. So in fact, what's happening is, when you have the current going up, there's a magnetic field around the wire, which, if you think about it, was part of the definition. We said when a charge moves, it makes a magnetic field. So there's a magnetic field. Now that title is wrong. It's not a solenoid here. It's a magnetic field around a wire. So the title, I suppose you should call it something more like... no, we'd have to make it a bit more formal than that. So we have bar magnet, the Earth. No, where's my picture gone? Picture 1. I must have deleted it or not put it in properly. I see I have 6 twice. Let me just have a look here. I can get it. 4, 3. Rats, I didn't save it. Come on. Come on. Anyways, we can draw the wire, but it's not called a wire. But now we know that one. We've seen that one, thank you. We've seen that one. That's the one I want. In a minute. That's number 5. Okay. So this one here, don't call it a solenoid, call it a current carrying conductor. The next one is called a solenoid. Alright, there is the picture there. So it just goes around the current carrying conductor. So really it's just a circle going around. So try and just draw this one here on the right. The one on the right. There's nothing happening in the first one. Current carrying conductor. Did you draw this? Yes? Let's see. Did you draw an arrow to show which way the current's going? The current's going up. Yep. Okay. Right, can I go on? Now the next one is what I wanted. It's called the solenoid. That's the next one I wanted. And here's the picture for it here. So it kind of helps to have both these diagrams side by side. So let me just show you what I've made. Before you draw, let me just explain the picture. So what you have on the left, can you see, again it's a wire, but the difference is the wire comes in and it's shaped like a spring and then comes back out on the left. And the magnetic field that you make when you run a current in this shape is exactly the same as a bar magnet with the north on the left and the south on the right. So just be careful about which way the current's going. See here, the current is coming in on the right and exits on the left, and it spirals. This makes the exact same magnetic field as the bar magnet with the north on the left and the south on the right. Okay, so it comes in, loops, and the current leaves. Also makes a magnet. So if you want to make a magnet at home, it's so easy. All you do is you take a battery, take the current, the wire, and wrap the wire around something made of metal. It helps. And then the wire just goes back into the battery. And then this thing here is now like a bar magnet. Yeah, we'll get to induction and things like that later, yeah. You know, this is what happens, you know when you see at the junkyard, it lifts the cars up, like this? That's what's happening here. So what they do is they turn the current on, lift the car up, then they turn the current off, and then it drops. Okay? So that's a solenoid. Yes?
You know, and the Breaking Bad.
No, I was thinking more of RoboCop with the junkyard.
In the one they put the junkyard and the magnetic.
Oh.
They put in the ambulance. Because you know they use it to destroy laptops in the police.
Yes. Oh yeah, okay. Now I was thinking more of RoboCop. Have you seen the original?
Yeah.
The very old one at the end in the junkyard. Okay, got this picture again. Now you just need to draw the one on the left. You don't need to draw the one on the right because you drew it already. solenoid, yeah. Did you get the spelling previously? Solenoid. Yeah, yeah. I can close this picture. Yeah, okay. Okay. Next. Right, so solenoid I showed you. It's not there. So we saw two things that may need clarifying. The last picture, which was the solenoid, and the magnetic field around the wire as well. So there's a little trick here to help you remember which way the magnetic field is going. So if I just go to the next slide. Come on. There we go. This is called the right-hand rule. So look, let me show you how it works. So you have, no, not that one. No, not that one or that one. So if you have a current, what you do is you hold the current and put your thumb in the same direction as the current. So if the current is going up, we hold it like this. And if the current was going down, you would hold it like this. Okay? The way your fingers are curved is the direction of the magnetic field. So if this is going up and we hold it like this, then the magnetic field is going around anti-clockwise as I look down. So this is called the right-hand rule or the right-hand grip rule. Yes, that's what KJ is trying to do. We'll get to that shortly. So this is the right-hand grip rule. Now, I don't expect you to draw this picture, but you can at least write down the name of the rule, which is the right-hand grip rule. Yeah? Okay. Continue. So the next thing here is a solenoid. So what exactly is a solenoid? Well, it's a coil wound into a tightly packed helix. So imagine a wire shaped like a spring with a current running through it. That's a solenoid. Helix is the name of the shape that a spring makes. Now, I always taught from school that not only does it need to be shaped like a helix, a spring, that there needs to be some iron running through it, or some metal running through it as well, around it. But actually, you don't need the metal there for the definition. But having a piece of soft iron that the wire is wrapped around makes it more efficient. But it's not actually part of the definition. But in real life, what you'll have is a soft iron core, and then the wire is wrapped around this. It makes it more efficient. Much more efficient. Yeah. Okay. Continue. You got this definition? Yes? Okay. So far, we have said absolutely nothing about the unit. So previously when we did electric fields, we measured electric field strength in newtons per coulomb, and we said nothing about the units for magnetic fields. So how do we measure magnetic fields? What's the unit here? So we have this thing called, okay, so just before I do the definition, these definitions are bad. Bad. And the reason they are bad is because you don't need to have them to be good for the exam. So the definition is not a great definition. The more formal definition is too advanced for this course, because the formal definition involves calculus and integration, things like this. Something you don't want in a physics definition at this level. So we'll just keep it as simple as possible. It'll be suitable for the exam. In fact, if I can just go back to the start for a moment. If I look here at what we need for the syllabus, I'm going to give you two definitions. The first definition is not on the exam. So I'll say that again. I'm going to give you two definitions. The first definition is not on the exam. This is good because the first definition is really technical and I'm giving you a stupid version of it. The second definition is on the exam and it uses the first definition. But because we don't have to worry about the first definition, we can pretend like it was defined properly. Get what I'm saying? So I'm giving you two definitions, but the second definition is what needs to be memorized for the exam, not the first definition. So I think it's fair that I tell you that. It's not part of the learning outcomes for the exam. Okay? So let me just go back. The definition I'm about to give you is not something they would ask you on the exam. Okay. So the magnetic flux over a particular area of space is the number of magnetic field lines passing through that area. The SI unit of magnetic flux is the Weber, which is the same as a volt-second. No, not volt per second, volt second. The symbol is important. The magnetic flux is this symbol phi. Yep. Worst definition ever. Because what I'm saying here, if I draw it, if you have a region of space, so let's say here, this piece, this area here, it's the number of magnetic field lines going through that area, so this here would be 3 Webers. Is that what I'm saying? So the definition is not great, but the way I put it to you is like this. The magnetic flux is like measuring how much magnetic field is going through that area. Yep.
How do we know how many lines in
Well, that's what I'm saying. It's the worst definition ever. How do you know? You don't know. Exactly. So this is my point. Worst definition ever. Okay. So we pretend like this was a good definition, but it's okay because we don't need it for the exam. So what do you need to picture here? The Weber, that's the unit, is a way to measure how much magnetic field is going through an area. So like for example, which way is north now? Which way is east? South? So the city centre is that way. Yeah, so north is that way, isn't it? You're gonna open up your compass. Isn't it north is that way?
Yes.
Just leave it, leave it, leave it, leave it. It's pointed that way, is it?
Yeah, like straight, straight.
No, see that's what I thought, but yours is pointing that way. But I thought it was that way. Because the city centre is that way. Yeah. So anyway, look. The Weber is like, I have an area of space, like this area here, and it's how many magnetic field lines are going through that area. So like, if the North Pole is here, and this is the area, you imagine the magnetic field going through this. You got the picture? Yes?
Like this.
There's a magnetic field going from here to the north.
The magnetic field affecting the compass.
Yeah, that's how a compass works. So it's like how many magnetic field lines are going through this surface right now. That's the magnetic flux over this area. Yeah? Yeah?
But the magnet that in the earth, it's
Yeah.
in the surface. The lines, the electric field is
Magnetic field.
magnetic field.
Yes?
So it's distance apart, right?
Yeah, it's quite far apart, so it's quite weak. So I mean, I think it would probably less than 1 Weber per meter squared, I think. Let's have a look at the next definition, which is on the exam. So that was magnetic flux, which is like a measure of how much of a magnetic field there is. And now we have something called the magnetic flux density, which is at a particular point in a magnetic field. It's the amount of flux per unit area perpendicular to the field. The unit is the Tesla, which is just 1 Weber per meter squared. Mathematically, you can relate the flux density and the flux with the following formula. The B is the closest thing we have which is comparable to the E for an electric field. No, don't snap it, write it down. Because the second definition is an exam definition. So this is an exam definition. So a Tesla, you've all heard this name before, Tesla, Nikola Tesla, the Tesla car. Tesla is just a Weber per meter squared. So it is literally like a density in that it's an amount per area, whereas density in mechanics was a mass per volume. It's the same thing. It's a thing per region of space. Yeah? So a Tesla is 1 Weber per meter squared. And it's important to to note that it depends where you are in the magnetic field. So for example, if here's my magnet here, and here is my north, and here's my south, the magnetic field is going around like this. If I'm here, the number of Webers per meter squared will be greater than if it was up here. Because the magnetic field, it doesn't go on forever, it shrinks. So the Tesla, it has to be at some point. Okay. So make sure you have this definition down. They'll ask the second definition in the exam. Have you got it? Yep. Okay.
You use D for density,
We can't because we've already used it for mechanics density. Yeah. So B for the flux density. Okay. So again, the B is the thing which we have that is like the E for an electric field. A bigger B means a stronger magnet. So, just like with the electric field, we'll talk about the formulas for force. A moving charge will produce a magnetic field. I said that in the definition. And by using the right-hand rule, we can know what this field looks like. So, for example, if I have a charge going from here to the wall, a positive charge, then if I use my right-hand rule, like this, the magnetic field is spinning this way. So as it goes to the wall, the magnetic field is going around it, like this. Now you know that when you have a north and a north, what happens? They repel, and a north and a south, they attract. A north and a south attract. So remember from middle school and life that north repels north, S repels S, but N and S will attract. So what's going to happen is, if the charge is moving, it will make a magnetic field. But if I have it in a bigger magnetic field, if the north is nearer north, what will happen? There'll be a force that pushes it away. But if it was a north near south, then it will be attracted. I'm not going to worry about the direction for now, but it is enough to know that when the charge is moving, it makes a magnetic field. This magnetic field, if it's in a bigger magnetic field, something will have to happen. It'll either move left or right or up or down. Just like when you have two magnets together, something happens. Okay? So the question is, how much force do I have? If I have a flux density, no, that's the wrong symbol. That should be a B. Let me fix that.
Have you ever tried by using 4 bars to like stay one bar here?
Say again? Have I ever tried what?
Put like in 4 directions, tip like north,
Yeah.
and middle is the north. It will stay in the air.
It's strong enough you can do this, but it needs to be really strong. Okay, let me just open this again. Does anyone actually know this formula? The force on a charge moving in a magnetic field. Maybe you know it?
Because
Do you want to have a guess?
The force on the charge.
In a magnetic field. What was the force on a charge in an electric field? Yeah. So if you were to have a guess, what do you think the formula for the charge in a magnetic field might be?
The charge is the force.
The force on a charge in a magnetic field. Go on. No? Huh?
Q?
No? That's charge. Alright, we won't commit to any guesses then. Fair enough. Well, in an electric field the force was QE, And what did I say the thing was that's like the E for a magnet? I just said it 1 minute ago. The B. Yes?
Yeah.
So what do you think the formula might look like?
QB.
Looks like QB. Now it is very much like it, but it's not exactly QB, but when you see the formula you might not be surprised. So if I just get back to it here. Come on, you can do it. Yeah, come on. Alright, so here we go. Formula is QV times B.
QB.
Yeah. Now, this V and B, you should write this multiply symbol down because it's a special type of multiply. So write it exactly like this, where cross is a special type of multiplication known as cross product. Now, it's not QB, but it's QVB, and the V there is actually important, because if you think about it, if the charged particle is not moving, will it make a magnetic field? No. So if the V is 0, what's the F?
Zero.
0.
Oh, the V is the
Velocity, yeah. So its presence makes sense. And also it makes sense that the faster it moves, the more of a magnetic field it makes, because a moving particle makes a magnetic field, so it's not surprising that more movement makes more of a field. No movement makes no magnetic field, meaning there won't be any force on it. You got this? Now I said that multiply is a special type of multiply because when you think about it, the V is velocity. Velocity is a vector. And the B is flux density, which is also a vector because it points in the direction of the field. But that's not important right now. What's important is how do we multiply these two numbers together? So for example, if the B was 2 Tesla and the V was 5 meters per second, well, multiplying them together it does make 20. But what the cross product does is it tells you which way the result points. So the next slide will be important here.
LeftHand rule.
Yeah, this one here. This is Fleming's left-hand rule. So let me explain this. If I go back to my example at the beginning, now which way did we say north was? North was that way.
Yep.
So which way is the magnetic field pointed? No, this way. Because we said on the Earth, the North Pole is where the south of the magnet is. So the magnetic field is pointed that way.
No. It's north to south.
Yeah?
This is north, this is
Oh,
south.
sorry. My bad. So the magnetic field is pointing this way still. Okay. So let's imagine the charge, we had a charge and the proton was released from the board and the proton moves across the room that way. So it's moving this way and the field is going this way. How much force will it feel? Well, we can use the formula QVB. So do we know the charge of a proton? Yeah. And we could know how fast it's going. And actually I know what the value is for the Earth. I think it's about a quarter, 0.25 Tesla. So we know the B. But which way will the force be acting on the particle? Well, this is Fleming's left-hand rule. So what you do is, this finger here is the magnetic field. So that we said is that way. This one here. Yeah. This finger here. This one here is the current, the charge, which nicely for me, the way I have it, is going this way. So the force is going up. So this means when the proton is released here, the magnetic field is causing it to move upwards. Okay? So this is what the cross product is for, or Fleming's left-hand rule. It tells you which way the force will act on the particle. So the formula tells you how much force, and Fleming's left-hand rule says which way the force is acting. We got this? Now, you can try and draw that. The current. By the way, if I replace the proton with an electron, which way will the force be acting? Up or down? Left or right? Forwards or backwards?
Down.
If I replace the proton with an electron,
Down.
the force will be going downwards because the current is going to the left now. The field is still going the same way. The force is downwards. So protons would move up and electrons would move down. And this is actually a way you can sort between protons and electrons. So imagine you had stuff coming here. If I have a big magnet, the positive stuff will circle up and the negative stuff will circle down. So this is actually, using a magnet is a way to separate protons or positive charges from negative charges. And this is something that you might hear about in chemistry. Which are, whatchamacallit, oh my goodness, what's it called? Thing with the electron gun.
Oh, color,
What is it called?
spectrometer.
Spectrometer, mass spectrometer, yeah.
Oh.
We will look briefly at that later too. So Fleming's left-hand rule. So we have the right-hand grip rule and Fleming's left-hand rule. Let's continue. So now we're in a position to have a look at some questions. So can we write this question down? Okay, sorry, there you go. Should we say over a particular region of space, but what else? Okay, can we have a look at this now? Right. So not crazy difficult to get started. What you have your magnet and you have your flux like this, flux line. And what I say in the question is there's a region of space which is a circle of radius 1 centimeter, and there's 2 Webers here. So what is the density? Well, no problem. Density is flux over area, which would be 2 over pi r squared, which would be 2 over pi 0.01 squared, which would be quite an extremely large value of 63666 Tesla. Or if you want, 6.4 kilotesla. Yeah. So here, that's what the magnetic flux density is. Okay, next question. It's a short question. In fact, I think I kind of already did it. Yeah, I did this one already. The proton moves towards, so if we look here at our compass, this way is north, this way is south, this way east, this way west. So if the proton moves to the east, which way will the force be on it? Well, left-hand rule, field that way, current that way, so force up. So the force is to the sky, upwards. So the answer here is upwards. So you don't need to write this down, we did it already, it is upwards.
The exam give you a compass.
No, they won't.
How do you know which is north?
Well, you just, on your page, write north, south, east, west, and say the top of the page is north.
So we
Yeah.
can make up in our notes and stuff.
Yeah, but I mean, usually what happens in the exam for these questions, they give you pictures, and they say which way is the force action, and they would draw this stuff. Okay, so a proton moves in a magnetic field. The magnetic flux density is the location of the electron. Oh man, why did I say proton and electron? Which do I want? I would like, let's make it, I'm tired of protons, let's make it an electron. So an electron moves in a magnetic field. The magnetic flux density at the location of the electron is 250 millitesla. The electron is moving at 1/10 the speed of light. What is the acceleration of the electron? So just make sure proton says electron here. Write this down. So everything's an electron here.
How are we supposed to know the speed of light?
It's in your formula book as a constant. We got this? Hold on. You'll be fine. I'm just changing my, here it is here, to electron. Right, that's the question there. Can I do it now? Come on, chop chop, what's taking so long? Chop chop.
Handwriting.
You know, if you hadn't messed with your handwriting like me, you could write faster.
I don't want to mess, I want to read it.
I want to read, but I don't want to be Chinese or anything.
Yeah.
What is the
Okay.
expression of the electron?
Yeah.
Okay.
Alright, time to do it.
Yes.
So, let's write down what we know. We have our formula, F equals QV cross B. But I don't care about the direction, so I'll leave the crossing part of Fleming's left-hand rule out. Do we know the charge of an electron? We do?
Yes.
It's on the calculator. Now the speed here is 1/10 the speed of light. Which, what letter is for speed of light? C. And the B, I said, is 250 millitesla. So, let me see. Shift 723 for the electron. So here I get F equals 4 times 10 to the minus 13 newtons. But that's not what I want. What was I looking for here? Acceleration. So Newton's second law says F equals ma. So that means the acceleration is this number divided by the mass. So if I divide my answer by the mass of a proton,
Electron.
no, it's not the same. Sorry, it's electron, isn't it? That's a minus 13, by the way. Electron. So I get here a huge 4.4 times 10 to the 17 meters per second squared. Now that value is too big, and what I mean by too big is the acceleration will very, very, very quickly decrease from this. So the acceleration is not constant, and it won't be as big as this. The reason it's so big is because the mass of the electron is so small.
So you made this number up?
No, the numbers aren't really made up. They're all realistic numbers. 10th of the speed of light. I mean, they're all realistic numbers, but what I'm saying is acceleration is never that big. I mean, it might be this big, but only for nanoseconds, and then it'll start to decrease. Because usually acceleration should be no more than 10 to the 7. So it's 8 orders too big. But again, it's not that it's too big, it's just it won't be this big for that long. The acceleration is not constant. But this is stuff we don't have to worry about. It's a little bit too advanced, just a little bit. But it is just enough for me to say that if this was really happening, the acceleration would very quickly decrease from this value. Okay.
No, hold up.
No, there is. I keep mixing up my articles in this homework and lesson. Let's just say demagnet lies on the y-axis. Whatever, so. Okay, can I close this now? Yeah? I'm closing it, yes? Okay.